this video, we're going to prove some theorems about property of inverses. The first proof, the first statement is, if A is a non-singular matrix, then A inverse is non-singular, and A inverse is just A. So, if A is non-singular, that implies A inverse exists. Now, how do I prove that it's non-singular and that A inverse is A? Well, if I prove that the inverse of this matrix exists, then it's non-singular. Now, suppose the inverse of A inverse is A. Then, now I don't care what this matrix is. If the inverse of this matrix equals that matrix, then when I multiply these two matrices, I should get I, and I do. So yes, the inverse, let me write it down slightly in a different order. So the inverse of this matrix is A, because when I multiply this matrix by A, I got the identity. Okay, and this also shows that, be exactly sure, this also shows A inverse is non-singular. Why? Because it has an inverse. Okay, now let us look at proof B. It says that if A and B are non-singular matrices, then so is the product non-singular, and this is true. Okay, so we want to show that the inverse of AB is B inverse A inverse. There's really one positive way of showing that. Multiply these two and show that they give you the identity. Well, AB times B inverse A inverse. We have dissociative property. I want to group the middle two. Notice I did not change the order of the four matrices. The middle two multiply out to A. I will invoke dissociative law again by multiplying the first two first, and then multiplying that by A inverse. A times I is A times A inverse. Why, that's A. Excuse me. That is I, the identity. So yes, AB inverse is B inverse A inverse. So not only did we show that AB inverse is this, we also show that AB is non-singular. Hence, AB is non-singular. How can you have an inverse if it's singular? It has to be non-singular. Okay, that is proof for B. Proof for C is if A is non-singular, then A transpose inverse is A inverse transpose, meaning that you can switch those two. So proof for C, we must show that A transpose inverse is equal to A inverse transpose. Okay. So, if I take AT and I multiply it by its inverse, which we claim is this, and I get back the identity, we're okay. We are okay. Now, the theorem that we proved that says that is C times D transpose, well, that's just D transpose C transpose. Well, we're in this form. If you switch the order, if you just take A inverse times A and you transpose that, you get equality. But this is I transpose, which is I. So, when I multiply these two, I get I. So, the inverse of this, which is that, inverse of this is A inverse transpose. So yes, the inverse of A transpose is what you multiply A transpose by, namely A inverse transpose, to get back the identity. And we don't need this for the proof. This completes the proof of these three parts for properties of inverses. If you like videos like this, please subscribe to my channel. I am always making up new ones. Leave a comment. State how much you hate my videos. I love reading those posts. State how much you enjoy my videos. If you want to see our theorem proved, state the theorem in a message, and most probably I will write up the proof for it. Thank you for watching, and as always, come back and watch and learn. Thank you.